I'm glad to be at this point in the day. Any questions about things before? Oh, you guys look like I felt this morning. Kinda. Well, happy Monday. It's been a Monday for me. Did you guys have a good weekend? No. Okay. Well, today we're going to hopefully finish up liquids. And next time, for the next couple lectures, we'll do gases on chapter 14. So, last time we did density. What's density? Mass over volume. Good. So it's both. And pressure? Force over area. Very good. And for fluids, that helps a lot because we don't want to add up all the little individual forces from all the molecules. It's easier just to take all those forces kind of in a lump sum over whatever area they're pushing on. So it works great for liquids. And not just the bottom, but on the sides too. The pressure is pushing there. And in a fluid, pressure depends on what? Density. Good. So something that's more dense, how would that affect the pressure? Which way? More pressure. If it's more dense, there's going to be more mass in the same volume. So it'll weigh more and exert more force over that same area. That will increase the pressure. So if you replace water with glycerin, maple syrup, something like that, it'll cause more pressure. What else does it depend upon? Depth. Very good. So it doesn't care how much water is there, just how deep it is. And the deeper you go in that fluid, the more pressure there is. Now, another concept is buoyant force. I'll spell it. It's still a force, and it's still caused by the force over an area, and it matters how deep you are. But this one you're familiar with. When you go swimming or you hop in the hot tub, right? You feel lighter, right? Or it's fun. You try to hold something up heavy in the water, and it seems easier. Why? The buoyant force. The fluid, in this case the water, actually provides an upward force that helps support some of the weight. And you can feel it just trying to push a balloon underwater. It resists. Why? Because, you're trying to push the water out of the way, displace water. So the water pushes back. Whose law is that? Which law is that? Very good. Newton's third law, action, reaction. You push on the water pushes back. And that force you feel is the buoyant force. It's the water trying to buoy it back up. The same thing applies, we'll learn next chapter, in air. There's a buoyant force on all of us right now because we're in the fluid displacing a certain amount of air because we take up space, and so we've displaced some of the air. And so there's actually a buoyant force on us right now. It doesn't make us float. A buoyant force doesn't determine whether it floats. We'll get to that. But that force is there. So, if you weigh yourself outside, you weigh so much. If you jump into a pool and stand on a scale, the reading will actually read less. Remember again, the scale is supporting, it provides the supporting force, a normal force, which is not always your weight. You haven't changed your mass, your weight's the same. But with fluids, we kind of call it an apparent weight. You feel like you're less. The scale doesn't have to push back as hard because the water's helping hold you up. So the scale will actually have a lower reading. So next time you're feeling overweight, especially around the holidays, you could try that, I guess. So, we can write that. We've already learned that. The buoyant force, I'll just F sub B. This is in the way for the moment. We're getting right to it. One way you can think of the buoyant force is your weight in air minus your weight in water. It'd be that difference, because that's what's helping hold you up. Simple enough? This would work in any fluid. We can replace water with just the word fluid. Because if you jump into a vat of mercury, it's more dense, a lot more dense. So it'll provide a different buoyant force. There'll be a difference in your weight in and out. But that's one way I'd like you to think of buoyant force. It's just that difference. Let's see what's going on a little better. Oh, yes. Can you buy it? Yes. Yeah, chemical supply stores online. You know, like if you're buying it for a lab or something.
Yeah, you don't need any licensing.
I never did when I did buy it. But I've always been at a university, and it might have been inherent and I didn't know. And I haven't had to purchase it in a long time, so it could have changed. But I never had to do anything fancy. They might make sure you're old enough. And, yeah, it could be a quantity if they're thinking you're going to poison something, but the quantity. I have some if you want. People, yeah, they're scared of it now that I've kind of been, that and lead around here. They're like, oh, I don't want it, I don't want it. Oh, can I have it? They're happy to give it to me. I have a mercury spill-up cleanup kit, too. So I know how to take care of it if it gets out of hand. It is toxic. You don't want to get it in your bloodstream. But
you can keep it in a cedar box, right? Or what's a good way to keep it?
I keep it in glass or certain plastics. It'll be fine. I prefer the plastic in case the glass breaks, but some plastics it can leach into. There's lots of different types. So let's see. This object is hollow inside, and this is the exact same volume. So here's a good demo in and of itself. Why is it taking so long to get in there? You tell me. It is going. Why is it taking so long? Yeah, it's pushing against the air in here and compressing it. What's that doing to the pressure? It's increasing it. It's trying to leak out the sides, but it's a tight fit. And so it's hard. Yeah, we're increasing the pressure. But it's slowly leaking out. There. So it's in there. It's the same volume. And it's hard to pull out, too, for the reverse region. That's always a good sound. Why does it do that? Well, as I pull on it, I'm increasing the volume here. Thus, that air can expand, and it's decreasing the pressure in there. The air in the room is pushing on this. And I have to pull against that. I have to do work against that. And once it comes out, that air rushes in and equalizes the pressure, and you hear that fun sound. All right. Because I've never been able to do that really well with my mouth, you know. Not now with the chalky finger. Okay. So that hangs. What's it weigh? We'll call it 2.5 newtons. That's its weight. If I hang this on here, we get what? Call it 6.5 newtons. Okay. I'm going to fill this container up with water to the brim. There's a hole. That's hence the tube over here. It drains out the hole when it leaks. Okay, there we go. So it's to the brim. I'll empty this. This is empty. There we go. So what's going to happen to this when I submerge this cylinder into the water? Yeah, the weight should go down. And why? Because of the buoyant force. It has a certain weight on its own, but the fluid, the water, is going to help buoy it up and help support it. So the scale only doesn't have to support its entire weight. And the difference in the two weights, the weight in air now versus the weight in the water in a moment, will tell us the buoyant force. Let's see what it is. Let's see, I'll just lower this. So we're at 6.5-ish. Put it in. You can see it's displacing water, pushing it out. Is the scale going down? Good, it's working. I'll make sure this isn't resting on the bottom. That's the bottom. There. You can see it still swings. Okay, what are we down to? 5? Okay, so what's the buoyant force? 1.5 newtons. Right. That's the reaction force of the water pushing back up on the cylinder. The cylinder's pushing the water out of the way. How much water did it push out of the way? This much. And so the water pushes back with 1.5 newtons of force. Here's Archimedes' principle. The weight of the displaced water, whatever this weighs, is the buoyant force. That's how it works. It pushed this much water out of the way. That determines the difference. So if we could weigh this, what do you expect it to be? 1.5. So I can pour it back in here. And it should be the exact same volume. I'll show you. So watch the scale, and I'll pour it in. Scale goes back up. Keep pouring. And there, it ran out right when it's on the top. Don't know how well you can see it. So objects, when they're submerged, displace their volume of water. So it's great. If you got an odd-shaped object and you want to know its volume, remember from geometry you could calculate lots of things, but what if it's funky-shaped? You just submerge it in water and see how much the water displaces. It would be that simple. You can fill a container, and if here's the water level, you throw the object in, and it's going to go up, right? Note that difference. That's the volume of water displaced, which is exactly equal to the volume of the object that's submerged. I think that's cool. It's good in cooking, too. Like when you got butter, and it's unmarked. Somebody already took the wrapper off. I don't know. Or it's mangled. Now, I do want to emphasize, if an object is only partially submerged, like this, it won't displace its entire volume of water. It's only what's underneath, this much. So the water will still get displaced, because that is pushing it out of the way, and it'll displace that much volume of water. Not the whole object's volume, but whatever is submerged gets displaced. You with me? And you can see that this went back up to 6.5. So yeah, the water that was displaced was exactly equal to the buoyant force. That's Archimedes' principle. I guess, let me empty this so you guys can see a little better. Any questions thus far? You now know pretty much everything you need to know to understand sinking and floating. We're just going to talk about it more to make sure you do. There. Does that help your vision? So, this is in your book. Archimedes' principle says that the buoyant force is equal to the weight of the displaced fluid. Because that's true in air and water, blood, whatever. So we displace a certain volume of air. How much? Whatever volume we take up, because we're completely submerged in the air. If you could take the air we displace and weigh it, that's the buoyant force on us, helping buoy us up. That's not going to weigh very much. That's not going to be a big contribution in air, is it? Because its density is really small. Water's density is a lot greater. So we see this effect more in water. So weight of the displaced fluid. What's weight? mg. So the mass of the displaced fluid. We'll call that dF for short. And with fluids, it's a lot easier to represent the mass in terms of density. So that's my next step. Density is mass over volume. So mass is density times volume. And I'm just going to put that in here. So the density of what? The object or the fluid? The fluid, because this is the mass of the displaced fluid. So it's the density of the fluid is what matters, not the density of the object. And the volume will be the volume of the displaced fluid, not the volume of the object, how much water is displaced. Because if the object's not completely underneath, it won't displace its entire volume. If it is completely under, then they are the same, but not necessarily always. And then gravity is gravity. So this one is a nice guide to thinking. But conceptually, this is just the weight of the displaced fluid in convenient form for us to solve things if we need to. Let me emphasize again, it's based on the fluid, the density of the fluid, and the volume of the displaced fluid. So if you replace the fluid with maple syrup, a swimming pool of maple syrup, besides being really sticky and hard to swim in, what else will you notice if you jump into it? It'll be hard to swim. It'll be hard to, it'll be hard to sink because the buoyant force holding you up is a lot bigger. Yeah. You'll float higher because the buoyant force is bigger. And the more you go under the fluid, the more fluid you displace. And so the buoyant force will be bigger. So as pressure was depth dependent, how deep you go, didn't care the volume, buoyant force is volume dependent. It really only cares how much water you're displacing, how much fluid you're displacing. Not necessarily what the object is. It could be really heavy. And it doesn't matter whether it's floating or sinking. You can be at the bottom of the ocean, like we're in the bottom of the atmospheric ocean, right? We're displacing fluid, correct? So there's a buoyant force on us, even though we're at the bottom. You can throw an anchor in the ocean and it sinks. But it's still displacing volume. So it still has a buoyant force acting on it.
Something in the book I didn't quite understand. They said if you had a life preserver and you stuffed it with foam,
That's a good one.
and the same life preserver, same area, and you stuffed it with lead, the lead you're going to sink.
Correct.
So I guess I was confused because
Yeah, the guy giving the person the life preserver in the book, it said, here's one of styrofoam, here's one of lead, they're the same size. Oh, you'll be fine. Well, he didn't say you'll be fine. He said, what? You're going to feel a greater buoyant force. And it was like the question, is this person pulling my leg? Is he joking with me? He's actually true.
so why is it?
Well, let me say why the buoyant force is the same first. Or you tell me. Two exactly identical life preservers. They're the same size, same volume, but one's full of styrofoam and one's full of lead. It has more density, so it has more buoyant force. Okay, I'm going to pause you there because I always got confused with this too. The buoyant force depends on the density of what? The fluid. So the buoyant force itself doesn't care whether it's made out of styrofoam or lead. What does it care about? Volume. And the volumes are the same. So buoyant force would be the same if they're the exact same size, whether it's out of styrofoam or lead. If they were both completely displacing the same amount of water, right? Because they'd have to be completely under to displace the same volume. In reality, what happens? Styrofoam vest, where are you at? You're floating on the top. You're kind of half out like this. So that's kind of like the styrofoam. And the lead, you're like this. You're at the bottom. So this one is displacing more fluid because more of its volume is under the water than the styrofoam one. And if you're displacing more fluid, you do have a greater buoyant force. Does that part make sense? So it is true, the lead life preserver would have a larger buoyant force because it's underwater and displaces more fluid. But the instructor, what he doesn't tell you is that, yeah, you sink and you're going to die. And that's my next point anyway, so let's do it. Get the shadow off of this. So let's go. What determines whether you sink or float? Nothing new. It's the same game. What forces are acting on you? Here you are in a fluid. Tell me the forces. Gravity. So you have mg down, and now we have buoyant force up. And if we're in mechanical equilibrium, these are, how do they compare? Yeah, they're equal. So basically, remember, we're just summing up the forces again. So you look at it this way. Let's see, let's do... if the buoyant force is bigger than your weight, we have the buoyant force less than the weight, and you can have the buoyant force equal to the weight. And I bet you can guess what happens. Buoyant force is bigger, you float. You see that? That would be, this is bigger. So the net effect is you go up. Yeah, you float. You come to the top. If the buoyant force is less, it's like this. Yeah, this one's bigger, your weight. So the net effect is you go down. You sink. And if they're equal, what happens? Do you go up? Yeah, you stay put. Neither. Neutrally buoyant, we call it. Now, floating is going up to the top. Floating's up top. So just hanging out where you're at. If you just stay put like right there, then the two... Yeah, you don't go up nor down. And if you took your hand and go... You neither go up nor down. You stay there. If you put it up here, it'll stay there. If they're the same. So the beauty about styrofoam is just that it's light. So in this case, the buoyant force is a lot bigger than the weight. So it's floating. Because styrofoam's light. Lead, say that's lead. It's really heavy. The buoyant force is bigger on this than this. So let's see. But it's heavy. Try to draw the scale. So sure, the buoyant force might be bigger than the styrofoam because it's displacing more fluid. But it's just too heavy. It's not enough to make it float.
So how do they get, like, big ships and steel?
I'm glad you asked, Ron. How do they make big ships out of steel float? Large area. Yeah, more specifically, not area, but volume. Yeah. It's density. Because you got the same amount of mass, it weighs the same. And you got a 20,000 Newton ship. Your ship weighs that much. If this is going to float, what's the buoyant force need to be? More than that. So if you see a big ship and you know how heavy it is and it's floating, you know the buoyant force must be that, at least. But to be that big of a buoyant force, it's got to displace a whole lot of volume, doesn't it? Volume of fluid. So they just take the ship and spread it out. So there's some pictures in your book. You can take a lump of steel like that. Doesn't displace enough volume to produce a big enough buoyant force to compensate for its weight. Again, I want to emphasize, Archimedes' principle is the weight of the displaced fluid. It's volume dependent, how much you're displacing. The more you can displace, the bigger the buoyant force. So then take that and reform it. Same material, just spread it out maybe, like this. That's going to displace a lot more volume. Not drawn to scale. So yeah, just make a ship really big and it'll float. What if you take a weight now, passenger, it's the Love Boat. And all these people get in here, right? And equipment and food and dance and everything. It gets heavier, doesn't it? mg's increasing. What's the boat do in the water? It gets lower. What's that do to the displaced water? It displaces more. If it displaces more, the buoyant force goes up, and that can balance the increased weight, right? It's really clever, I think. Laws of nature. So sure, you make this heavier. Oh, we need more buoyant force. Well, it naturally sinks in and displaces more fluid to compensate. Until the water level rises over the edge, this way, and there's a limit. Boats can only hold so much weight. If mg gets too big for its volume, it can't handle it. So that's how to think of sinking and floating in terms of buoyancy. Now let's look at it in terms of density, because there's an equal way to look at it that way. I might as well just put it back up here. If the density... Let's do it over here, I guess. I ran out of room. The density of the object, the density of the fluid. Density of object, density of fluid. Density of object, density of fluid. Greater, less than, equal. Let's see what happens. If the object is more dense than the fluid, can you see that it will not displace enough volume to compensate for its weight? Because all its mass is concentrated in a small volume, it's dense. More dense than the fluid that's trying to exert a pressure on it. So this will sink. It's another easy way to just look at density. You with me? Does that make sense? Say they had the same mass, but this is going to do it in a smaller volume, so it won't create a large enough buoyant force to make up for that weight. Where the opposite, if the object is less dense than the fluid it's in, it will float. And this, it'll just stay there where it's at. This one's fun. It's pretty easy to do. Fill like a Ziploc bag. It's really light. Doesn't contribute much. Fill it completely full of water. Like put it underneath, fill it up, and seal it off. When you let go of it, it's pretty much water in water. And the density of water compared to the density of water, the bag kind of just sits there, hovers. And you can see this example. Let a little air into the bag. Seal it with a little bit of air. What will that do to the bag's overall density? It was all water, now it's water and air. Yeah, it lessens it, because air's density is less. It's part of its air now. And so you let a little air in, and now it's less dense than the surrounding water, and it'll float. It's like when you go swimming, you take a deep breath, right? You fill yourself full of some air. It's hard to stay underwater. You float back up. most people. But a nice trick, you want to stay on the bottom of the swimming pool for a while. Blow some of your air out, not all of it. What are you doing to your density? Yeah, you're increasing it. And so at some point, you let enough air out, you'll be more dense than the surrounding water as a whole, and you don't have to you don't have to fight to stay down. You can just stay down there. Of course, then when you want to come back up, you have to fight. But okay, good. So 2 ways to look at it. And I'll just get some more examples here, because this confuses some folks. Wet. All right, these 2 cylinders are balanced, full of water, the same weight on each side. If I throw this ball on this side, what will happen? It'll float? I'll give you that. Yeah, this will float. It's full of air. It'll float. You can see that. It's like the balloon. What will happen to the scale? Yeah, stay put. How come? If it floats, it won't displace water? Okay, then what's making it float? The buoyant force. Good. Buoyant force makes it float. What creates the buoyant force? The displaced water. So this will displace a certain amount of water, which means it has a buoyant force. So it will have a buoyant force. Yeah, that's why it floats. Some of it will go under the water and displace. However much is displaced, remember, if we weigh it, that's the buoyant force. So yeah, it'll feel a buoyant force. So why does that keep them equal? Or do other people disagree? What do you think?
I think it's going to go down. It's going to weigh more by how much water is displaced. Whatever small amount that is, it's going to be the weight.
So it's going to displace water, but it's going to stay in the same beaker. So we're not changing the amount of water. We add this to it. We're adding weight to it. But the water's holding it up.
Yeah, but like it doesn't matter. Still, like, if you look at like the two, you're adding weight to one side of the scale and not to the other. So it's going to go up a little bit.
That's right. You're adding weight to one side or the other. Let's just do it. Ready? Yeah, you've added weight here. Now the water is supplying a buoyant force. We covered that. That's holding the ball up. So why does the scale have to go down?
Because
the weight of the end that belongs also add weight on the boiling force on the other side. That's why the other side is more heavy than the side if you don't add the weight.
That's good. Good point. You want to add to that?
You're making the water slightly deeper, which would increase the force.
We're making it deeper. There's more of it now, but there's the same amount. So its weight hasn't changed. The weight of the water hasn't changed because there's the same amount there, even though we changed how it's distributed. Yes, Ron?
I remember when you put the book on the table and you said even though it's sitting on the table, gravity is still pulling down on the book itself.
Yeah.
Maybe it's doing the same thing.
Gravity is still pulling down on this ball.
Right, even though it's being supported by the water.
That's right. And it's being pulled down. What gets in its way? The water. The reaction force to that is what? This is pushing water out of the way. The reaction to that is the buoyant force, pushing back up. That's the reaction. I got more, but we got a comment here.
I don't know if you gave away the answer yet, but what I was going to say is that...
I'm almost there.
Okay, so, I mean, since the water pushes up on the law of buoyant force, because third law pushes back on the scale, so that's what pushes it.
Very good. That's exactly what I was going to say next. So gravity pulls the ball down. The reaction is the ball pulls the earth up. That's the pair. But, okay, it's coming down. The water feels that force. It displaces some of the water. So the water reacts and pushes back. That's the buoyant force. Well, if the water is pushing up, the reaction to that also is the scale gets pushed down. You can't just... if you're like floating in space and you push on something, what happens? You need like a reference, right? We're on ground. So when I push, what's keeping me in place? Friction between me and the floor. Let's think of it that way. So the water's pushing up, which means it gets pushed down against the scale. And ultimately, yeah, this has weight. You can't get it back out. This weighs something, and that's how much more it goes down. But it's through those processes to help us understand this buoyant force. All right. What will happen? No, they're balanced. I dip my finger in it. What will happen? It's kind of the same idea, but the finger's connected to me. I'm holding my finger up, right? The ball wasn't being held up. I'm holding my finger, but I'm just going to stick it in there. I won't touch the bottom. I'll just kind of submerge it a little. Now, then what will happen? Go through the process again in your head. Will I displace water? So there'll be a buoyant force in which direction? Upward on my finger. What will be the reaction to that buoyant force? Just like with the ball. In order for it to push up, it's going to get pushed down. So, it goes down. All right? And I'm not touching the bottom of the beaker. So it's just to really emphasize that buoyant force is there. Because I'm displacing fluid, how much determines the buoyant force? But it's up. To react, this gets pushed down. I think that's cool. Let's do some more. Here's some examples. My fish tank of science. Start with this one to emphasize density again. Sink or float, what do you think? Well, you guys are great. Because, okay, we'll go that. How's its density compared to water? It's floating, so the density of the object, the boat in this case, is less than the density of water. All right. It's not the aluminum. It's not the density of aluminum. Because I spread the aluminum over a large volume. That big volume allows a big enough buoyant force to overcome its weight. So over here, it's floating. The buoyant force is bigger than its weight. That's why it's floating. Okay? Let's change its density, shall we? There we go. Now what will it do? Not as much. So it's still floating, so everything we just said is still true. The density of the ball, how's that compared to water? It's still less. Because there's air trapped. It's still kind of poofy. But can you see it's floating lower? That means it displaces more water. The buoyant force on it now is bigger or smaller? Bigger. It needs to be to overcome its increase in density. Okay? Let's make it more dense. All right. What do you think? Not yet. Okay. There we go. So now, same matter. It's had the same mass all along. But each time we changed its volume. Now its overall density is greater than that of the fluid. It is not displacing enough fluid to have a buoyant force large enough to compensate its weight. It's completely submerged, so it still has a buoyant force. It's just not enough for its weight. Regular A&W root beer diet. Most diet sodas float. You tell me. Tell me what you know. You're observing what must be true. Yeah, there's a difference between sugar and the sugar substitute. That's what'll get to it. And that changes the can's overall density. Which one's less than water? The diet, yeah. You ever see it really is lighter, right? No, I'm not lighter, less dense. These have the same. No, they're the same volume, aren't they? So the masses must be different. Because this one's less dense and this one's more dense. This one does not have enough buoyant force. They displace. How do the buoyant forces on each one compare? How do the buoyant forces on each one compare? But this one floats. Bless you. It's the same buoyant force. They're the same volume. What does buoyant force depend on? The volume that's displaced. Notice, though, this one that doesn't completely submerge. So he actually doesn't displace as much volume as that one does. So in reality, the regular soda has a bigger buoyant force. But it's still not enough to compensate for the difference in weight. Cool, huh? And you're right, it's the sugar. This one has so much sugar in it. This one's replaced by less sugar substitute, which tastes in theory just as sweet, but it takes up less space. So it makes it less dense overall. That's the gist, anyway. Concrete. Same volumes. Concrete can float. If you make them differently, this one must have more air in it. It is. It's lighter. If you come up here, you can feel there's less mass for the same volume. So same idea. And again, who is feeling the greater buoyant force right now? Yeah, the one on the bottom, because he's displacing more fluid. Doesn't mean he floats, but he is displacing more fluid. All right. This was a toy when I was a kid, and they still make it. It's one of those little diving subs. So what you do is you take baking powder with your wet fingers, and you put it in this the container at the top. Good enough. So I filled the inside with it. It's open to the fluid down here. There's like a mesh. Seal it off, or close it up. You put it into the water, you shake it a little so it reacts with the water, and then you watch. Bloop. The water and the baking powder have a reaction, and it turns into a gas, but the gas is trapped in the submarine. So here it sinks. It's a bit more. Oh, now it's coming back up because the gas was forming. And then you watch it closely, it'll tip, and you'll see a bubble come out. Bloop. Well, that's releasing some air, which makes it more dense, the submarine. And that's how submarines work. Well, they don't. Bloop. They take on more water or release water in and out of their tanks. That changes the overall density. And that's how they can control whether they sink or float. And if they want to just hover there, what density do they match? The outside water. Yeah, they take on enough water or off so that the overall density is the same as water and they can stay put. Bloop. Kind of fun. Another one is ketchup packets. Some of them work. They're full of ketchup and an air bubble inside. So you can mesmerize your nephews and nieces or younger siblings. Because if you just squeeze the bottle, you can make it sink. Try to do it this way so you can see better. These are less dense than I would like. If they start out just less dense than water, you can just kind of squeeze without anybody knowing. But not these today. So what's happening? You exert pressure on the bottle. It exerts pressure on the ketchup packet. And it's like squeezing it. So the air bubble that gets trapped inside the packet with the ketchup gets a little smaller. Its overall density increases. And it sinks. Let's do it this way. Air bubble small. And when I let up, they rise back up. That's called a Cartesian diver. There's another version. These little pump caps you can buy to protect the fizz in your drink. It adds air to the bottle, which increases the pressure. It's like me squeezing the side. This is a little eyedropper I filled with blue water. And if I increase the pressure enough by adding enough air, it pushes down on the top. And at some point, there it goes. I've decreased the airspace in there, changed its overall density, and had it sink. Last but not least, we'll do the fun one instead of clicker questions, I guess, today. And that is the only thing we didn't get to, and it starts leading it right into the next chapter. That's where we'll start next time, is Pascal's Principle. Pascal's Principle. We'll repeat it next time. But the idea is you can exert pressure on something. You can blow air, but we're going to trap it in this container here. And remember the formula for pressure at the beginning? If you do pressure as force over area, we're just kind of switching it around. Pressure is force over area. So what we're going to do is create a force. This has a certain amount of pressure. It's not enough to hold anybody up. It won't lift you up. Low pressure. But times a big area like that, you can get enough force to lift somebody. So if you just kind of get on here, turn it on. Woo! So that's kind of the basics behind hydraulic lifts. That's the last thing in Chapter 13. We'll talk about this a little more next time and move into the fluid of the air. Take care.